The best sorting algorithms we have seen so far were merge sort, which has time complexity of O of n log n, and quick sort, which is quadratic in the worst case. However, an important version of quick sort reduces the worst case time complexity to O of n log n. Here is another advanced sorting algorithm that takes advantage of heaps. The idea of heapSort is simple. Assume you have already all items to be sorted stored in a heap. Now we start removing the elements one by one from the heap. The first removed element will be the smallest one. The second removed element is the second smallest one, and so on. In other words, the elements will be removed from smallest to largest. So we fill an array from left to right with the elements as they are removed from the heap. The result will be the wanted sorted array. Since the remove operation on heaps is logarithmic, and since we need to call this operation n times to remove all elements, this sequence of n removal operations takes O of n log n time. The only problem is that the array to be sorted doesn't generally represent a heap. So we have to build a heap first from an array of arbitrarily arranged elements. Let's go through an example to see how a heap can be built. Assume we have the array with the 7 elements, 5, 3, 9, 4, 8, 6, 1. We can interpret the array content as a complete binary tree where the elements in the array represent the binary tree elements in level order, just like in a heap. But the corresponding tree is in general not a heap. Now look at the leaf nodes and interpret each leaf node as a tree consisting of a single node. Each of these single node trees is also a heap by itself. Interestingly, about half of the nodes are leaf nodes. Now we go one by one through the nodes in reversed level order and turn the tree rooted at the corresponding node into a heap. Eventually, we will reach the root node and turn the tree rooted at the root node into a heap. Then the entire tree is a heap. So let's get started. The first node that is traversed is a 9, as the leaf nodes are already heaps. So we need to turn the tree rooted at 9 into a heap. Note that the two subtrees of 9 are already heaps. Only the 9 might be out of place. We actually solved this kind of problem before when we looked at the remove operation for heaps. In that case, we replaced the root by the last leaf node and then used the heapify operation to get the new root node to the right position. We can apply the heapify operation here as well to node 9. Note that the heapify operation can be applied to an internal node, not only to the root node of the original tree. Of course, it only restores the heap property to the tree rooted at the node 9 in this case. Applying heapify means that node 9 is swapped with its smallest child, which is 1, resulting in the following tree. Now we move on to the tree rooted at 3 and call heapify for node 3. Since 3 is already less than its two children, 4 and 8, the heapify operation will not swap any nodes. Finally, we move on to the root node, node 5. Observe that now the two subtrees of the root node are heaps. We call again heapify for node 5. Node 5 is swapped with its smallest child, 1. Since 5 is less than its two children, 6 and 9, no more swapping takes place. The final tree is a heap. Here's the pseudocode to build a heap. We first determine the index of the internal node that comes last in level order. Since half of the nodes in a tree are leaves, the index of that internal node can be calculated as n-2 over 2. So index I serves as the index of the node for which the heapify operation is called. Traversing the nodes in reverse level order means that we go through the nodes in the array from right to left, starting at index I. We know that the heapify operation takes O of log n time if it is called for a node whose subtree has n nodes. Heapify is called about n½ times, so a straightforward upper bound for the time complexity is O of n log n. Surprisingly, one can show that the procedure is actually linear. That means we can build a heap in linear time from an array. Let's summarize how heapSort works. An array is sorted by first building a heap. This can be accomplished in O of n time. Then the elements are removed one by one from the heap and inserted into an array from left to right, resulting in the wanted sorted array. The second part takes O of n log n time. So O of n log n dominates the runtime. That concludes the last sorting algorithm we look at in this class.